Okay, so Philip's question is about how do we calculate the trail slope alignment angle for the trails exercise that we did and recorded in Thompson Woods the other day. So I'm going to go ahead and share my screen and capture that. All right, so can you see actually we could just use a whiteboard. Yeah, there we go. All right, so you can see just the whiteboard screen for the moment.
Mm-hmm.
Cool. Perfect. All right, I'll get the toolbar out of the way. And the basic idea here is I'm just going to kind of recreate the exercise from the beginning. And then from there, we'll be able to hone in on specifically the angle calculation part. So
It's still loading, actually. I'm not quite getting anything quite yet.
oh, okay. Let's all right. Can you see the whiteboard screen? Or is it?
Yeah, I see it now.
All right, cool. Very good. Sorry for the technical hangup. I'm reaching that age where I'm going to have to ask young people to program a VCR. All right, so we've got most people oriented the map bottom to top. So at the bottom of the screen, hopefully you see an X for trailhead. And that is just an arbitrary landmark. So we used a field stone, in the field lab, but for folks doing this at home, this will be kind of anything. And this is just going to be a trailhead kind of conceptual feature more than a physical one for us. All of these practices apply in the middle of a trail network away from edges of the trail system and trailheads as well. And then kind of at the top end of the screen, I'm going to place another X. And this will be kind of our just sort of destination site. And again, this is a conceptual thing. So this could be a point of interest like a waterfall or a waterfall viewing platform or a backcountry campsite, that sort of thing. And that is pretty flexible. Every park, every wilderness area has typically dozens to hundreds of points of interest of varying sizes and pull, so to speak. Some geographers would call them gravity features, since they tend to kind of pull people's interest towards them and suck them into that gravity well. All right, so label that destination. And then we basically had in our setup, and this will be important for the angle calculation, the idea that there's kind of a hill increasing in elevation between our trailhead and our destination. In practice, typically the landscape is a lot more complex than that, but for this first exercise, just wrapping people's brains around the concept of it, it's a pretty simple setup. So you can imagine it just like a simple flattened but tilted plane or slope, not a compound curved surface. And then from there we have a trail that kind of meanders through the woods a little bit. And the basic instruction for that first trail alignment was to, as long as you're not walking in somebody else's footsteps, kind of take any path that you want to get between the trailhead and the destination to reinforce the idea that along the de facto path that each person walks, we're accumulating one set of tramples or trampling impacts along that path. And maybe the ecosystem is vigorous enough to rebound from that with only a total of one trample per plant along the way. And maybe it's not, with either very, very fragile plants, and we'll get more into what those might be later on, or a whole bunch of people trampling along that same track. So many, many tramples on the same individual plants, a lot more damage, and they can't necessarily bounce back from that. And then along the way, mark, I'm just going to sort of freehand sketch these in so they'll be a little bit messy. Just pick some arbitrary spots. I'm getting mostly approximately even distances between them, but you can kind of put them wherever you want, maybe a half dozen, maybe a dozen points. And then at each one of those points, draw two short arrows. And since our hillside, we're considering our destination sort of a local peak, or prominence. One of those two arrows is going to be pointing directly uphill, and in this example, that's going to be directly toward the destination, X. So go ahead and draw those in. And this was all done freehand sketch map in the field, so we're doing it the same way here. In a GIS environment, so computer mapping, of course, this is going to be a lot more precise, down to a very, very tiny decimal of a single degree, or a fraction of an arc second. And get that last one in there. These are not the aspect, these are actually the back azimuth for the aspect. So the instructions were to draw a series of points along the trail, 6 to 12 of those. Again, this is more for concept than detailed math. So after that, for each one of those points, I want to draw an arrow pointing directly upslope. In this case, toward the destination.
This is mine that I drew up last week. It's kind of messy, but I think it was pretty rugged. The points that I made were towards the side. Is that generally okay?
Yeah, that's fine. I can see what you're doing there, and as long as you are getting the concept, it in a digital sense, like the arrows aren't even going to be on the map. They're going to be in a table attached to the map, but not labeled on the map. Right. But some people hate GIS, so this is a user-friendly way to kind of introduce the concept. So those points are, or excuse me, that first set of arrows are technically called the back azimuth of the hill slope aspect. So 180 degrees off of the direction that the hill is facing. So when you're standing and looking directly down slope, that's the azimuth, or the facing of the hill. We're looking directly up the slope, so it's the back azimuth. 180 off of the azimuth. And then, of course, the other arrow is pointing directly along the trail, or parallel to the trail if you're drawing it as you were, kind of off to the side there. So in this case, we don't really even have to draw the stems of the ears. We can just draw the heads. And for the second point closest to the bottom, or the penultimate point, I will basically place that arrowhead just behind the other one, since the hill slope and the trail are both pointing directly at the destination for that particular point. And then the next step, which sounds like what you were asking about, is the what's the angle between those two, and can we get some kind of a useful bit of information out of that? So next we were going to draw the direction of the trail at each point with a second arrow, and so forth. All right, and you could use different color if you're doing it digitally, or just kind of sketch it in, and you can kind of see which arrow is which, hopefully. So this is the tread or trail azimuth at that point, and that's a constantly varying number. It can be anything between 0 and 360 at any point, completely regardless of the trails, or the hill slope that the trail is on. But the issue is that for certain ranges of angles between these two arrows, we have a really erosive situation. And at the opposite end of that spectrum, where the value of the angle between those two arrows is fairly large, between 75 and 90 degrees, that's a very sustainable trail routing relative to the landscape. So the trail doesn't care what its compass direction is. It does have to care a whole lot about what direction it is relative to the steepness of the slope. So the next and kind of final step with this part of it was to sort of just guesstimate the angle formed between the two arrows using back azimuths. If the angle is greater than 90 degrees. All right, so let's do a couple of examples, and I'll do these off to the side so it's a little bit easier to see what's going on without the trail sort of cluttering things up. So if we have an angle that is, let's say again that the hill slope is running or increasing in elevation towards the top of the screen or the top of the window. The landform arrow would be this way, and when we have let's see, when we have a trail that is running straight up the slope, that is literally the channel morphology, the geofluvial morphology, or the study of the shape of a river channel. That's the definition of a channel, when the lineal feature is running straight up the slope. So if you zoom way in on any topographic map anywhere on the surface of the earth, all natural streams and rivers, anything that's flowing fluid, even lava flows, they literally have to flow straight downhill for that particular spot, which means that they're always crossing topographic lines at a perfect 90-degree angle every time. So if you zoom in on the map, that's what you'll always see. This is exactly that sort of definition. The opposite case, so this would be, let me label this, can I close the loop here? This is a trail slope alignment of 0 degrees. And very unsustainable. And so to kind of show the opposite situation, we have down at the bottom corner of the screen, hill slope running straight vertically, and the trail at that particular spot is going sideways. So it's actually slabbing or iso elevation. It's staying very level instead of going straight up the slope, gaining or losing elevation as fast as possible according to the landform. In this case, it's going straight across the landform, and if you keep following whatever imaginary contour line is kind of under your feet at that spot, the trail never gains or loses elevation. That's what defines a contour line. And if you're walking up like a mountain on this trail, and the trail suddenly becomes a contour trail like that, or an iso-elevational trail, you'll go all the way around the mountain and back to that same spot without ever having gained or lost any elevation. And water, again, doesn't care about the trail or anything. It just has to flow downhill, so it's going to go across that very quickly and very sustainably. It's going to leave the soil of the trail in place and be good to go. So let's label that one as a TSA of 90 degrees, max sustainable, or max sustainability. Now, if folks want to get to the destination, we can't just use iso-elevational trails. They're lots and lots of fun. The Mont Blanc circumnavigation trail goes around Mont Blanc up at elevation, and it's a blast. You get to see these beautiful, beautiful mountains in Europe from basically every angle. You literally walk in a circle and then you go away. But, you know, there's always going to be a lot of people who want to get to that peak, see the views, watch the sunset, propose, you know, whatever. So eventually that trail's got to climb up the slope. And so that gives us the question, very important question of, okay, so how close can we sort of tilt the trail up to run up towards the destination? How close can we get away with before it gets super erosive? And it turns out with a whole bunch of measurements that we did back in the 90s and 2000s in field research, that cutoff is going to be about 75 degrees off of vertical. So I'm freehanding it, but it's going to be about 15 degrees off of the right angle. So it looks about like this.
Okay.
And that's going to be TSA equals 75 degrees. And we'll label that as the worst we should try to get away with. So that's gonna mean a very long, winding trail, lots of switchbacks going up and down a slope. Done well, it doesn't feel like a very regular, constrained, boring zigzag. People don't love perfect predictability out in the wild. It feels very kind of manicured, you know.
Yeah.
So the only confusing part, I think, and I'll diagram that in while I'm sort of getting this this last example in. So this next one will be a 45 degree angle ish off of both the direct ascent running straight towards the destination and also 45 degrees off of the contour line at that spot. And this is not sustainable, but it's very common. Let's see, with older trails that are not designed to survive. All right, so TSA equals 45 degrees. Too aggressive. All right, and so all of these angles here, as I've diagrammed them, are between 0 degrees, 45 degrees, 75 degrees, 90 degrees. But what they don't show is, what happens if, you're estimating your angle and I shot my compass straight up the slope and I got 0 degrees, pointing towards true north or magnetic north. And the trail in that direction is at 171 degrees. So almost completely the opposite direction, almost running straight downhill. In that case, you'd have, I'll move to the other side of the trail for space here. We've got the hill slope and something running like 170, 175 degrees away from that. The trail slope alignment angle for a 175 degree angle formed by these two is actually only 5, because remember, we take the back azimuth of the trail if the TSA formed by the original pair of angles is over 90 degrees. So the trail is running upslope and downslope. If in this case, the downslope arrow is pointing more than 90 degrees away from the upslope arrow, then we'd just face 180 on the trail and look up the trail instead of down it and use that compass direction and subtract those two numbers. So that would be 355 degrees, which is 175 plus 180 to get it to the other side. And compare that against 0 degrees, which is the same as 360, and subtract the smaller from the larger, and we get a 5 degree trail slope alignment angle. So let me put that into text. That's the only confusing part, and I promise that's it. All right, so
Okay.
TSA equals 175, so it really equals, let's see, 175 plus 180, which is only 5 degrees off the hill slope. So the true TSA is 5 degrees. All right. Clear as mud? How you doing?
It makes a little sense. I'm still trying to grasp the math a little bit, but I get the idea.
Okay, so let's, all right, I've got that whiteboard saved, and I'll upload that to the course website along with this video, and then I'll go ahead and clear it, and we'll get into the math just a little bit more. Okay.
It was like the first trail that I drew up seems to be a little bit more realistic than the next one. I wonder what I did there.
So what do you mean by realistic? Let's kind of unpack that term. That can mean a lot of things.
Based off of what you said, like having a trail on a straight line would be just not good at all. And so the second one that I did was a little bit, it wasn't as curved.
Yeah. Okay.
Yeah.
So, but it's got kind of that snake shape, that sort of waving back and forth.
Yeah. It was very much a snake shape. There were a couple really wide turns, but it's straighter than the other one.
Yeah. Snakes are good. Now, you'd never hear me say that as a Gryffindor, but so the term we're going to use in technical trail design for this is sinuosity, or how much the trail curves per unit forward length on the trail. Sinuosity. Right. So let me put that term here on our whiteboard. Sinuosity is the degree trail curvature in either direction. It could be, left or right. Snaking does both. Right. Degree trail curvature per unit trail length. So rivers, for example, are measured on this as well. And a river that is rapidly flowing down a slope, like a whitewater river, with more than a couple of degrees slope, is typically actually going to go fairly straight. And then when you see a river hit a very flat area, like an alluvial plain or the river's delta area, it gets these crazy meanders and oxbows, and it'll cut itself off, like the worm will cut off into oxbow lakes as it moves along, and it'll just constantly meander within the confines of its steeper banks, the upper tiers of the river basin. But for trails, we want to use that sinuosity, that left-right migration up and down slope, to do exactly the opposite of keeping a river inside of its channel. We want to get the water off of that trail as fast, as effectively as we can, without having it be so fast that it actually takes the surface of the trail with it and erodes everything and kills a bunch of stuff down slope. By sediment transport and stream blowout and habitat destruction, it can be pretty bad. All right, so with a super straight trail, any water that gets entrained or stuck in the trench that the trail tends to form is going to be stuck. There's no way to get water off of that, because it's carving out its own basin as it goes and just deepens it, and makes it muddier and easier to erode. If now we're looking side on instead of down at the trail from above, if the trail kind of meanders upslope and downslope a little bit, we haven't gotten to this in class yet, but this is actually a formal trail design feature that's very important and allows us to avoid stuff like having to cut and maintain over and over forever stuff like water bars, which everybody hates. They're a tripping hazard. Horses hate them. Mountain bikers really hate them, and stuff like that. So if the trail just kind of meanders up and down slope a little bit, any water that gets trapped by the trail here, well, it cannot flow up and out. Water does not flow uphill, so it has to exit right here. And we can make sure that there's no berm or sort of catchment lip on the low side of the trail at the bottom of the dip down here. So these rolling grade dips and rolling grade reversals are the two kinds of features combined here. If you sort of design these in and then cut in the trail properly the first time and cut in the rolling grade dips and reversals, that's it. You barely have to maintain that trail kind of ever after that, unless it's of a couple of specific soil types that just will never hold together like pure sand. This is all getting ahead. So this is kind of the underlying super secret reason why we are starting to think about these trail slope alignment angles. But this constant change of trail slope alignment angle gives us these design features and this sustainability for free. So that's why the second attempt on our exercise, part of the instruction was to see if you can make the trail kind of wiggle left and right a little bit as you go. See if you can make it meander through the woods. Take it to some point of interest along the way. That kind of forces you to not beeline it straight to the destination, which is pretty bad. Okay, so that's kind of that's the subtext. But again, we'll get there in class with everybody. And let's work on the math a little bit more until that feels crystal clear. There's no funny business here. This is all very straightforward circle math or trigonometry. And once you kind of grab hold of it mentally and see it, you'll never lose it. It's like riding a bike. All right, so we've got the hill running up towards the top of the screen, and then trail running at 90 degrees, which also again means that the trail is running 180 degrees off of the first trail arrow. So in both of these cases, the trail slope alignment angle is 90, but it's also 90 on both sides of that. Right? Basic supplementary angles. So these two sum to 180 degrees because the trail has to be going forward from that spot and it has to be going back from that spot, unless it's the end of the trail and then it's only got one direction and we don't worry about that. So that's a sustainable contour trail. And then if we got a trail that is, so the hill slope's running straight up slope, and we got a trail that's in this particular spot, maybe it is, let's see if I can, there we go. All right, it's running 45 degrees sort of off of that and pointing down slope. And the back azimuth for that trail is going to be running 45 degrees off of horizontal and off of vertical. So what's the angle between the hill slope, which its compass direction for our just easiest math purposes would be 0 degrees on the compass, and the downward to the side pointing arrow looks like its compass azimuth, if north is up, would be 135 degrees. I'll label this for you. What's the angle formed between 0 and 135 degrees? Not a trick question.
Sorry, say that one more time.
What's the angle formed between the landform on this example, which is the vertical arrow at 0 degrees, and the angle and the trail, which is running towards the compass direction of 135 degrees? What's the angle formed between 0 and 135?
I'm a little stumped on that. I apologize.
Yeah, no problem. So it's 135. It's the larger minus the smaller.
Okay.
All right.
Got it.
But PSA, for our purposes, to keep all of the mental math simple out in the field, because we can memorize 0 to 90 numbers or 75 to 90 super easily. But if we get into the whole 360 degree math of it, that's when we're trying to do like math out in the field, when we're slapping bugs and hot and sweaty and we're carrying heavy equipment. We've been out there for 2 weeks and our brains are shot. We would actually look for the smaller of the two angles here because the trail runs both directions. So 135 degrees for trail angle. So 135 TSA. And let me let me label our numbers because I'm changing a little bit what each of these numbers represents. So azimuth. Azimuth is compass direction. All right, so if we are heading in the compass direction of 135 degrees, so going down slope in this case, and then we stop and we say, wait a minute, this angle is too big. It's 135 degrees off of the direction our hill is climbing in. So we stop and we turn 180 degrees to get that back azimuth, which is the upward pointing arrow, but not the vertical arrow. What azimuth is the trail also running in addition to 135? So that'd be 135 plus 180.
Uh, 315.
That is correct. So I'm going to label that one as 315 azimuth. And there we go. That's a little easy to read. All right, now 0 azimuth is the same as 360 azimuth. So what is the angle formed, or the other TSA formed between 315 and 360 degrees? Or it's exactly the same thing numbers-wise as 315 angle formed with the azimuth of 0.
45, right?
45, yeah. All right, and so the last step is sort of the interpretation of all of this. What have we got ourselves into with this trail? And we know what the number is, but managers, we're going to care about what is the interpretation. What do I do with this information? So given that a TSA of 75 degrees to 90 degrees, sustainable. Anything below 75 degrees, not sustainable.
Mm-hmm.
What's our conclusion for this little spot on the trail? Do we need to fix this? Or is this part of the trail going to be fine long term? Is it going to cost us a bunch of money and work over time? Or is this pretty sustainable, in other words?
Could you repeat the degrees one more time, please?
Sure. So I'll put the kind of reference table down here. So TSA greater than 75 degrees. Sustainable.
Right.
Greater than 75, but less than 90.
Greater than 75, less than 90. So 45, it wouldn't be sustainable.
That is absolutely correct. Less than 75 degrees, erosive, and eventually unsafe.
So that would mean I did some calculations on my end here. Judging by that, it looks mine wouldn't be sustainable either.
Well, if your TSAs are fairly small, then yeah, that's a real possibility. And it only takes 1 or 2% slope to have water flowing, and it's a self-reinforcing process. So it's going to take advantage of whatever help we give it by cutting an eventual stream channel in as a surface. We see it as a trail. Water sees it as a stream surface. If it's the easiest way down slope, it's going to go that way. And that's okay. So you guys are not being graded on providing me trails that are, 7.5 degrees TSA all the way through. You guys are being evaluated on, okay, am I getting this idea of what what is a trail slope alignment angle in the first place, and why does Park keep banging on about it? Like, why does he care so much about this? Because physics do not care about our hopes and dreams, is basically the answer. So we can try a lot of sophisticated things that look pretty cool on a trail plan or grant application, like we're going to put in all these stone stairs and all of these things, and we're going to truck in gravel, and we're going to hire and train this expert trail crew to maintain this. But if it's a total disaster in terms of design, then you have to do all of those things instead of putting that money towards 5 times as many miles of trails. All right, so let me add just a little bit more notation to our sort of exercise here. Angles are usually denoted with this little arc between the two arrows that form them. Now we know what those numbers are. So since this was just a sketch map, I wasn't going to have anybody bust out a compass or a protractor. Again, we just do all that stuff with a click of a button in GIS anyway, but the important thing is to understand the math going into it. What's the principle underlying this? What's the justification for this? Instead of, can you punch the right numbers in a GIS?
Right.
Okay. So go ahead and tally up the ratio of 75 and greater TSA points on your trails versus less than 75 degrees. And whatever the answer is fine. Like, you're not going to get in trouble again for having a trail that mostly runs straight towards the destination, because that is literally everybody's first instinct. And I'm not going to beat on you guys for that.
Okay. Yeah, it makes a lot more sense now. I think I get it. Yeah.
Cool. All right.
Okay. Perfect.
Yeah, and that'll underpin everything else we do about trails and campsites coming up. So we'll come back to this, and we'll have some more chances to kind of practice with it. But also, like on our field trip, for example, we'll do a couple of stops along the way as we're backpacking along to say, okay, how does this trail look right now? Why does it look good? Why does it look bad? Why are my feet wet right now? When we're not anywhere near a stream, there are basic physical reasons for it, and TSA is a huge part of that discussion. That's like the lion's share of it right there. So once you got this, you've got a lot.
Okay. Cool.
Do you think it would help if I got some like different colors of modeling clay? Do you think it'd be helpful if I had like a 3D version of this? I could like cut into a little hillside and make tiny little trails and show them on camera and be like, this part's sustainable. Let's pour some water on it and see where it goes,
Yeah, I think that would be a really good model. Yeah.
Okay, cool. Maybe I'll work on that this afternoon. So, what else? These are great questions, man.
Yeah.